All right, so the way this is going to work is that I want everyone to watch the video. I want everyone to take notes, but then the homework with this is going to be kind of optional. This has appeared on the AP exam. It's something that I want you guys to know, but it's a little more challenging. It's something where honestly most of you guys could get a 5 whether you remembered it or not, but it's easy enough, so I want us to at least take notes on it. There is not a spot in your packet for it, so you are going to have to take notes separately, like on another piece of paper, maybe staple it at the end of your packet, something like that. But we're going to kind of jump into it. So what the weird cases are is they're cases that just don't involve polynomials, right? What we looked at, like when we talked about limits at infinity, where we looked at cases, even if they were harder cases, something like this, like x squared minus 4x to the 5th over x cubed plus x squared. And in this case, you know, what are our biggest terms? Our biggest terms are, say, the negative 4x to the 5th, and x cubed. If we want to get rid of these other guys, we can. In this one, in this case, it's going to be negative infinity, because when, you know, if you cancel out a cubed, you get x squared, but this negative 4 is going to make it so that this limit goes to negative infinity. Those were all with polynomials. What the weird cases are going to be is when we don't have polynomials. Maybe we have something like the limit as x approaches infinity of e to the x plus 2 over x squared. Or maybe we have something like the limit as x approaches infinity of, you know, ln of x over x squared. And so these are a little bit of, you know, kind of more nuanced examples. So the pattern is going to remain the same. And that pattern was, you know, kind of this table that we had copied down. Where we said, okay, if the top is bigger than the bottom, really we should say numerator bigger than the denominator, but I'm just going to go with top bigger than bottom, top equal to bottom, and when the bottom is bigger, when the top is less than the bottom. So in this case, the first case when the top was bigger, it was infinity or negative infinity. You just had to kind of plug it in to figure out which one, and there was no horizontal asymptote. In this case, it was a over b, and the horizontal asymptote was a over b. Now, you know, the negative could appear if there was a square root, right? This isn't really going to happen with these weird cases because those are more for polynomials, but I'll just rewrite it. And then in the bottom case, it's 0 and y equals 0. So what we have to do is we have to figure out when is the top bigger, when is the bottom bigger for, you know, e to the x or ln of x or even sine x, cosine x. So we're going to start by looking at the graphs, okay? I'm going to just make kind of one big graph, and we're going to graph them next to each other. So first, let's graph, you know, y equals e to the x. Okay. Now, for polynomials, it could be x, it could be x squared, it could be x cubed, but they're all going to kind of be in the same area. So I'm just going to do y equals x. But, you know, x squared would have worked. X cubed would have worked. But I'm just picking y equals x to represent our polynomial. So x to, like, say, the first power. And then, you know, next one, let's do y equals ln of x. So this is at 1. It should pass through 0. And those are our main ones here, but I'm also going to actually add on, you know, trig, which would be sine x. Cosine x could work as well. And so, right, that's not perfect. It really should be nice and smooth, but what we know is this is at positive 1, and this is at y equals negative 1. So what's happening is I want to look at what's happening as we go out to infinity. Well, where is out to infinity? Out to infinity is all the way to the right side. Well, all the way to the right side, what happens for e to the x? E to the x looks like it's getting biggest the fastest. X, you know, or x squared is getting bigger next fastest, and ln x is lagging behind. And then for sine, it's really just bouncing between 1 and negative 1. So e to the x is getting, we're saying, biggest the fastest. Right, y equals x, like our polynomial case, it's kind of getting biggest, you know, to infinity, kind of in the middle. y equals ln of x is getting biggest, going to infinity, kind of the slowest. And then sine x actually never gets to infinity. So sine x and cosine x, they actually just bounce, or we'll use a better math word, we'll say they oscillate between -1 and +1. So, if we talk about, I like the where Sebastian said, like, which infinity dominates. If we talk about, like, which infinity is going to dominate or take precedence, is that our e to the x is going to dominate the most. So it's going to be the biggest. Then x to a number, right? And this could be e to the x, or it could be, any number to the x, right? It could be like 4 to the x, 5 to the x. But that's going to dominate x to a power, and that's going to dominate ln of x. Now, sine x and cosine x are kind of a special case. I like to just treat sine x and cosine x as 1, right? You just treat it as like a number that you can kind of ignore. So, you could kind of put it in here, but you want to be careful about these, because if they're on top, they don't go to infinity. Like, they don't. So you want to be careful. But if, they're always the smallest, right? They're always like way, way, way the smallest, because they're just kind of, you're treating them as if they're like the biggest they could ever get is to 1. Okay? So what happens is if we were just, let's even go back actually to these examples we were talking about. So, okay, now what's the biggest in this case? Well, e to the x's are biggest, and x squared is our biggest here, but e to the x is bigger, so it's going to either be going to infinity or negative infinity. Well, if we plug it in, e to the infinity is positive, so it's positive. Here, what's bigger is x squared is bigger, right? We said, which ones take precedence is x squared would be this one, is bigger than ln of x. So x squared is going to take precedence. So in this case, our bottom is bigger. In the bottom bigger case is 0. So that's kind of a couple, examples there. And we'll just look at some more examples, some kind of harder ones. What if we had y equals sine x minus ln x over, say, 2e to the x. And they wanted to know what is the limit as x approaches infinity of just y. And they can write it that way. And what they're saying is, what is the limit as x approaches infinity of sine x minus ln of x over 2e to the x. Remember, I said kind of treat sine x as if it was just 1. The biggest it could ever be is 1. Now, e to the x is bigger than ln of x, so this is going to be 0 because the bigger one was in the denominator. Now, where this does get a little bit trickier is with negative exponents, okay? And we want to be careful about those. So if we have the limit as x approaches negative infinity of e to the x, this one's actually tricky, okay? This is not infinity. This is actually 0. And the reason this is 0 is you want to be very careful about negative exponents, right? Negative exponents flip between the numerator and the denominator. So we want to kind of just remember as a side note that x to the negative second is the same as 1 over x squared. So e to the negative infinity is the same as 1 over e to the infinity. And with limits, what that kind of means is that the limit as x approaches negative infinity of 1 over, let's do positive infinity. The limit as x approaches infinity of 1 over e to the x, that's going to go to 0 because the bottom is bigger. So when we have this, what happens is when we plug in the negative infinity, we get e to the negative infinity, which becomes 1 over e to the infinity, which becomes 0. So we want to be extra careful about any time we have negative exponents. Now, it could happen that way, but it also could just happen like this. The limit as x approaches, say, even positive infinity of 2x minus e to the negative x over x squared. And you might be tempted to see this problem and say, oh, that's the biggest, it's going to infinity. But it's not. And the reason it's not is that this negative power, we can treat this as 1 over e to the x over x squared. right? You can't move this to the bottom because the 2x minus part is blocking it, so you just kind of make it its own fraction. Okay, and now if we plugged in infinity, what happens is when you plug in infinity, I'm going to kind of leave this as an x for right now, but when we plug in infinity here, 1 over infinity, that's the bottom case, right? That's that bottom case going to 0. So this part goes to 0, if that makes sense. And so now we have, okay, what's actually bigger, 2x or x squared? Well, the bottom is bigger. So the whole entire thing goes to 0. Okay, but it's because we had first canceled out that. So now when we plug in infinity here and here, the bottom guy's bigger, it goes to 0. So, I guess maybe we'd write limit as x approaches infinity here, even though we haven't plugged it into those guys. So, that one's a little bit tricky, but just watch out for that. And so what happens is, I think we're on example 4. You might get that all over the place. You might get the limit as x approaches infinity of x squared minus ln of x plus 1 over x cubed, all divided by 2x squared plus 7 sine x. And so this one looks hard at first, and it kind of is scary. But just remember, anytime you have 1 over x cubed, whenever you plug in infinity here, right, the fraction with the x in the denominator is going to go to 0. Okay, and then for the sine x, we're going to just kind of treat it as the biggest it could ever be is 1. So now we want to think, what are our biggest terms? Well, this is smaller and this is smaller. So in this case, it's actually that a over b case, and so we would get 1/2. I know these are tricky, but just the more you do, the better you get at them. So, kind of another example. Maybe we have the limit as x goes to negative infinity of 2x squared plus 7 sine x over e to the x. And again, you might be tempted to initially think, oh, this is 0 because the e to the x is the biggest. But be very careful, there's a negative symbol here. So because of the negative symbol, what happens is this is going to flip sides. Okay, and you want to be careful when it's in the denominator. You can do something like this. It's going to flip up to the numerator. So when you plug in that negative infinity, it's going to go up. So this actually doesn't even have a denominator. They're all in the numerator. So this is going to go to infinity. Right? And you can kind of get this by plugging it in. 2 times negative infinity squared plus 7 sine of negative infinity means going all the way out to the left. But again, the biggest that's ever going to be is 1. 1 times 7 is 7, so we're going to kind of ignore it. All over e to the negative infinity. Right? So we're going to kind of ignore this guy. And so this is 2 infinity squared over e to the negative infinity, and that's going to pop up, and everything's big on top, so it's a big infinity. That's pretty much all of our cases. The one other weird thing that I've seen, I've only ever seen this on Calc BC, but I'm just going to go over it anyways, is if you got something just kind of really, really funky, and I wrote one down that was similar to something that I saw in one of the BC exams, and that was the limit as x went to negative infinity of the square root of, say, 9x to the 6th plus 2x squared, and then minus x cubed outside of the square root over 4 minus 2x cubed. Okay, and this one is not actually one of those weird cases with e to the x ln x, but it's one of the weird cases with square roots. So we want to first kind of pick out our biggest exponents, and our biggest exponents are actually, that's an x cubed exponent. When we square root x to the 6th, it becomes x cubed. That's x cubed and that's x cubed, right? Anytime you do, right, like the square root of x to the 8th, it's x to the 4th. Square root of like x to the 6th is x cubed. You're kind of dividing by 2 when you cancel those out. So in this case, I'm going to just kind of start off by, let's just kind of ignore these guys. So this is kind of like having the limit as x approaches negative infinity of the square root of 9x to the 6th minus x cubed over negative 2x cubed. You cannot cancel these out yet because of the square root of 9x to the 6th. Now, what's the square root of 9x is 3, or 9, the 9 part is 3. And then we're not going to write 3x cubed, we're going to write 3 absolute value of x cubed. And the reason we put it in absolute value is kind of what I was talking about in class, where the square root of x for functions is just the positive side. So no matter what the answer is going to be positive, okay? And so even on the negative infinity, because it doesn't exist, what happens is the answer becomes positive. So we just have to be careful about that. So when we plug in our negative infinity, I kind of like to just do it like this, is just say, okay, that's 3 times the absolute value of negative infinity cubed minus negative infinity cubed over negative 2 times negative infinity cubed. Well, this is going to become 3 times the absolute value of negative infinity minus, right, when we cube this, it's going to stay negative. Negative infinity. You could have cubed, I guess. But that's going to turn it positive all over. And again, this is going to be negative, like negative 2 times negative infinity cubed, right? Because when you cube it, it's going to turn negative. So when you multiply them, it's going to turn positive. But now, when we do the absolute value part, that is going to force it positive. So 3 infinity cubed plus infinity cubed, all divided by 2 infinity cubed. And that's like kind of having 4 infinity cubed over 2 infinity cubed. So the answer is 2. Okay. And I know that's funky the way I plugged it in. Another way you can kind of think of it is just, when x is less than 0, it's going to basically take that, the negative and kind of flip it, force it positive. But you can't just, what I've seen a lot of students do is they just say, oh, 3x cubed minus x cubed over negative 2x cubed. And then that gives them 2x cubed over negative 2x cubed. And they get the answer of negative 1, and that's wrong. And the reason that that's wrong is they didn't do the absolute value part. So I know this one's tricky, it's a little tough, but you really just have to plug it in. You could kind of think with signs if you want to think with signs. A lot of people I've seen do that. They say, okay, what happens when I plug in negative infinity? It's going to, because the absolute value, it's going to make it positive. So 3, positive 3 infinity. What happens when I plug in negative infinity here? It stays negative, but minus another negative infinity. So that becomes 4 infinity in the numerator. And then what happens when we plug it into the denominator? Well, it becomes negative, but times negative 2 is going to be plus 2 infinity. So 4 infinity divided by 2 infinity is 2. Right? I dropped the cubes because at this point they don't really matter. Everything's the same. So that's kind of how that one works. I know it's tough. There is one on the extra credit that kind of looks like that. But again, I've never seen it on the AB exam. So if this last part was way too hard for you, don't worry about it too much. The key is, on our AP exam, most of the questions that I've seen look like these first couple examples. Sin x minus ln of x over 2e to the x. And we say, oh, the 2e to the x is bigger, so it's 0. I have seen this one a lot of times with this negative needing to flip, but that's as hard as it really gets. Okay, so this extra credit, like the video was mandatory, but the extra credit assignment is 13 questions. I do have the answers at the bottom, so you can do this by Thursday, like basically before the test. But it starts off with some of these square root ones. Then we get into some like this. Number 5 is different. Number 5, x to the 2/3 over x. Just think about, like, what power would x be, right? 3 over 3. So is 2 over 3 bigger or is 3 over 3 bigger? And then obviously down here, kind of that order of dominance, right? X to any power is bigger. and then ln of x, right? E to the x is bigger than x to any power, and then sine and cosine are the smallest. I don't think I have any sine and cosine on here, so don't worry about those too much. So if you want to give this a try, great. If not, don't worry about it.